In this lesson, we're going to talk about gravitational potential energy. You'll be able to outline the concept of potential energy and specifically calculate the gravitational potential energy of an object. So first, it's helpful to think of potential energy as positional energy. Potential energy is energy stored in a system, that is a collection of objects that we're thinking about together, by virtue of the relative position of the objects in that system. So for example, if we are lifting a brick above the Earth, then it's the relative position of the brick and the Earth. If we have two charged objects, then it's their position relative to each other that is storing potential energy in the system. And if we have a bow and arrow, then it's the relative position of the ends in the middle of the drawn string that are storing energy in that system. That last example may be a stretch, pun intended, in terms of thinking of it as two objects, but it's still true that potential energy is related to the position of objects in the system. Now, potential energy can also be converted into kinetic energy, and that's why it's potential. It has the potential for being converted into kinetic energy. We've got a number of different kinds of potential energy, including gravitational, elastic, electric, and magnetic. Let's start with gravitational potential energy. If we imagine lifting a box at constant speed, i.e. with no acceleration, we need to supply an external force equal to the box's weight. So let's say I have a box here, and it has a weight here equal to mg. If I want to move it upwards at constant speed, once I've got it moving, then the upwards force that I need to apply, let's call that F external, supplied by my hand, has got to be equal and opposite to the weight. So it's also got to have magnitude mg. And if I move that up through a displacement, let's say I move it up here so that it ends up there, then that displacement is the change in height. So the displacement is the change in height of the box measured from the same position on the box. Now, if we think about our formula for work, the external work that I've put in with this force, the force of my hand, is equal to the force that I supply times the displacement that it goes through times the cosine of the angle in between them. And because they're in the same direction, it's an angle of 0. Cosine of 0 is equal to 1. So the force that I've supplied, the external force, as we said, is equal to mg, and the displacement is equal to delta h. Cosine of 0 is 1, and what I've got is that the work external that I've supplied is equal to mg delta h. And that work is stored now in the relative position of the box and the Earth. The Earth is down here somewhere. And it would get released if we let the box fall closer to the Earth. It would get released as kinetic energy. So what we've seen then is that that work was stored as gravitational potential energy. In other words, the change in gravitational potential energy was equal to mg, that was the weight of the object that was countered by the upwards force, times the change in height. This was our displacement. So the change in gravitational potential energy is equal to mg times the change in height. By the way, note that the net work in the example above was 0. We had a downwards force doing negative work on an upwards moving object. That downwards force, the force of gravity, was equal and opposite in magnitude to the applied force. The applied force was doing positive work, pointing in the same direction as the displacement, and the force of gravity was doing negative work of exactly the same magnitude, pointing in the opposite direction of the displacement. Angle 180 degrees, cos of 180 degrees is negative 1. So the net work done was 0, and so the kinetic energy didn't change. Remember that by the work energy principle from the previous lesson, the net work equals the change in kinetic energy. No net work, no change in kinetic energy. Also notice that it's change in height that matters, not absolute height. And we need to set a reference height from which we measure all the other heights. That's how we get our change in height. And we can set that wherever we like. Also notice that the gravitational potential energy depends only on the initial and final heights, not on how the object got there. So raising an object from this lower height to that upper height like this is one change in height, but I get exactly the same change in height if I move it like this, up and down, up, and eventually end up at the same height. That's the same delta H, therefore it's the same change in gravitational potential energy. Finally, just remember from how we started that as soon as we talk about potential energy, we're referring to a system of multiple objects together. So any forces that are occurring between those objects, for example, in this case, the gravitational force between the box and the Earth are going to be internal forces. And that's going to become important later on when we're thinking of conservation of energy. So that's an introduction to potential energy and specifically gravitational potential energy.